Today I'm going to be talking about indefinite integrals and area, and specifically I'm going to get into a little bit of sigma notation, um, which we'll talk more about on Thursday, specifically in the context of finding the area under a curve. Okay, so reminder, you've got homework due Monday night, and you should vote today if you haven't voted. I voted. Where's my sticker? It's over there. But I voted. All right, so last time we left off on this example. So we throw a ball directly into the air with an initial velocity of 20 meters per second, and we're on top of a building that's 30 meters tall. Assuming the acceleration due to gravity is minus 9.8 meters per second squared, which it is, when does the ball reach its highest point? So to solve this problem, you're starting off with A of t. Well, A of t is just the constant negative 9.8. We want to know, when does the ball reach its highest point? That's a position. So I need to end up at S of t. Well, to go from A to V, the velocity, I need to take an antiderivative. So V of t, I need to take the general antiderivative, negative 9.8 times t, plus some constant. That constant is very important here because it's going to help us incorporate the initial velocity. Okay, so the initial velocity, I throw the ball. We'll say that this experiment starts when t is 0, so that means v of 0 is, well, when I plug in 0 into here, I'm going to get 0 plus c. And I know that v of 0 should be 20 meters per second. So that tells me c is 20. Okay. So then, let me erase this. So then v of t is negative 9.8 times t plus 20. And really, we don't need to get s of t. I'm going to write down s of t just so that you see the practice of getting another antiderivative. But when the ball reaches its highest point, well, if we think about it for a second, if you throw a ball in the air, it has a positive velocity up until it reaches its highest point, and then it starts falling down, and it has a negative velocity. So it goes up, 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 positive velocity, stops at its highest point, it has a velocity of 0 there, and then it falls, it has a negative velocity. So really, to find when the ball reaches its highest point, that's just going to be when v of t is equal to 0, which tells me that negative 9.8 times t plus 20 is 0, or in other words, negative 9.8t equals negative 20, so that t is equal to 20 over 9.8, which is a little bigger than 2, but about 2 seconds. Okay, and then if you wanted to find what the highest point actually is, well, then you would take an antiderivative of v. Well, an antiderivative of negative 9.8 times t is, well, to get a linear function, I had to have started as a square function. But when I differentiate t squared, I'm going to have a 2 come out in front. So I want to divide by that 2 so that I don't end up with 2 times t when I differentiate instead of just t. Okay, so I get negative 9.8 over 2 times t squared plus 20 times t plus some constant. And notice I didn't put a constant for this antiderivative and this antiderivative, because these constants are all arbitrary. So when you add, you only need to add one constant at the end. Take the antiderivative of each, or an antiderivative of each part separately, and then at the end, you can just add your constant of integration. Okay. And then we know that we start this experiment at the top of a 30-meter building. So S of 0 is 30, but S of 0 is also just this C. This C is not this C. In fact, I'll call it C1 just to be safe. So this is C1. Okay, so S of t is equal to Well, 9.8 over 2 is negative. That's going to be 4.9. So negative 4.9 t squared plus 20t plus 30 gives me the position function. And so again, if you wanted to find out the highest point that the ball reaches, that's going to be s of, well, the ball reaches its highest point at t equals 20 divided by 9.8. So s of 20 divided by 9.8 tells you what the highest point is that the ball reaches. But I didn't ask you for that, so if you want to find this, you can, but we don't actually need to. The true answer is t equals 20 over 9.8 seconds. Okay, so this is how most projectile motion problems will go. You'll start with an acceleration. You can integrate twice to get position. And along the way, you'll get those constants of integration that you can solve for using initial conditions. Okay. So, example, find the antiderivative, the general antiderivative of sine of x minus cosine of x. Okay, well, if you think back to the table that I showed you, this is going to be the integral of sine of x, and then just minus the integral of cosine of x dx. We know, let's look at sine of x. We know that the derivative with respect to x of cosine of x is negative sine of x. So I want to end up with positive sine of x over here. So that tells me that the negative derivative of cosine of x is equal to sine of x. So if I then integrate both sides, I end up with that the integral of sine of x is negative cosine x. So I'm going to get the integral of sine of x is equal to negative cosine of x. Similarly, we know that the derivative with respect to x of sine of x is just cosine of x. So if I integrate both sides of this with respect to x, I end up with the antiderivative of cosine of x is sine of x. This side I'm just left with sine of x. This side I'm left with antiderivative of cosine of x. So that tells me the antiderivative, the general antiderivative, or the indefinite integral of sine of x minus cosine of x with respect to x, well, that's going to give me negative cosine of x and then minus sine of x plus my constant of integration. Do not forget the constant of integration. It is very important. So let's move on here. Solve the following differential equations. So I need to look at dy dx with respect to x. You just integrate both sides of this to find the solution of this. So the integral of x squared plus secant squared x dx, right? So the integral of a derivative on the left, I'm just going to be left with the original thing. I'm not going to add my constant over here. I'm going to add the constant over on the right-hand side. So, because again, you don't need to keep adding a bunch of constants. You can sort of combine them all into one constant, okay? So this is equal to, well, to get to x squared by differentiation, I needed to start at x cubed. But then if I differentiate x cubed, I'll have a 3 out in front. So I'm going to divide by 3 to get rid of the 3. Okay, plus. And then secant squared x, although it looks scary, is just the derivative of tangent of x. So the antiderivative of secant squared x is tangent of x. Okay? And then I will add my constant of integration on the right-hand side. Okay? And then we have y of 0 from this initial condition. We can actually solve for c. Y of 0 is, well, 0 cubed over 3 plus tangent of 0 plus c. Well, this is just 0 plus 0 plus c. But we also know y of 0 is 0. So that tells me y is just equal to x cubed over 3 plus the tangent of x. Plus 0. I didn't forget the constant of integration. The constant of integration turned out to be 0 in this case. Okay. So this next problem, you're going to do this type of problem quite frequently where it might look bad at first, but if you rewrite this integral in this form and then simplify the inside of the integral, this x over square root of x, that's, well, this is x to the first divided by x to the 1/2, so I'm going to be left with x to the 1/2. And by the same token, 1 over x to the 1/2 is just x to the minus 1/2 dx. And now these guys, you can both for both of these, you can use the opposite of the power rule for differentiation. So if I just need to figure out what did I differentiate to get here. Well, in order to get to an x to the 1/2, I had to have started from x to the 1/2 plus 1, which is x to the 3/2. But then remember, if I differentiate this, I'm going to get a 3/2 out in front. So I need to multiply by 2/3 to cancel the 3/2 that will be out in front when I differentiate. So I'm only left with x to the 1/2. Okay? And then by the same token, I'm going to get plus. Well, if I end after differentiating, if I end with x to the minus 1/2, I had to have started from x to the minus 1/2 plus 1, which is x to the positive 1/2. But then again, if I differentiate this, I'm going to get a 1/2 out in front of x. So in order to cancel that and only be left with a 1, I'm going to multiply by 2. Add my constant of integration. And you can verify that this is actually an antiderivative of x plus 1 all over the square root of x by differentiating. So if I differentiate this, I'm going to get 2/3 times 3/2 times x to the 3/2 minus 1, which is 1/2. So those cancel. Plus 2 times 1/2 times x to the 1/2 minus 1, which is minus 1/2. Those will cancel. And c is a constant. And so I'll be left with x to the 1/2 plus x to the minus 1/2, which is exactly what the inside of the integral looks like. So that's verification that this is indeed the correct antiderivative. Okay. So last problem as far as antiderivatives go, if we want to find the general antiderivative of 2x e to the x squared, that problem is something we're going to deal with later, probably next week. But if I tell you, well, I think the antiderivative is this, it's very easy for us to check. So to check that this is the antiderivative of 2x e to the x squared, I can just take the derivative of what's on the right, and if I get what's on the inside of the integral, then it is indeed the correct antiderivative. So let's take the derivative of e to the x squared plus some constant. Well, that's going to be a chain rule for this. So the inside function here is just x squared. The inside is x squared, and the outside is e to the x, right? So the derivative of the outside with respect to x is e to the x, and the derivative of the inside with respect to x is 2x. So then the derivative of e to the x squared is the derivative of the outside, e to the x, evaluated at the inside, so e to the x squared, and then times the derivative of the inside, which is 2x. And then the derivative of the constant c is just 0. So I'm left with 2x e to the x squared, which is exactly what we wanted to be left with. So this is the e to the x squared plus c is the antiderivative of 2x plus x squared, the general antiderivative. So that's all the types of problems you'll see on the homework involving antiderivatives. So we're also going to look at areas under a curve. And so in order to do that, we're going to need a sort of special new notation called sigma notation. Okay, but first, let's talk about sort of what the whole second half of calculus is all about. So the second half of calculus is called integral calculus. The first half was all about finding a tangent line. Essentially, if you boil all the problems down to the very bare essentials, all the problems that we've done so far, it essentially was find the slope of the tangent line. Okay? The second half of calculus is interested in, instead of finding the slope of some tangent line, we want to find the area under a curve. Okay? This is a problem that especially the ancient Greeks were really interested in finding, say, the area of a circle. Well, if you graph the semicircle, you can find the area under that and then multiply it by 2 to get the area of a full circle. Okay? So some drawings of what we're doing in Calc 1. Here's some general curve. If I want to know what is the equation of the tangent line at x equals 1, well, we found that this was just, if this point was 1, f of 1, then the equation of the tangent line is y minus f of 1 equals the slope of the tangent line, which we found was f prime of 1 times x minus 1. So if you really boil down all the problems that we've done so far, they were all about finding that line. The second half of Calc 1 and all of Calc 2 is about finding the area under this curve. So we have, this is the same curve, y equals f of x, and we're finding this blue area between x equals, in this case, x equals 0 and x equals 4. But in general, we want to find the area between x equals some number a and some other number b, and then between the curve and the x-axis. Okay. So we can do this in the case of, say, straight lines. If this was just a horizontal line, well, then this is just the area of a rectangle. If this was, say, this straight line here, that's just the area of a triangle. And if I move this triangle up a little bit, well, then you can say the area of that shape is the area of a trapezoid, or the area of this rectangle plus that triangle. But if once we start adding general curves and trying to find the areas of those, then the problem becomes much more difficult. But the idea in finding these is just going to be to use rectangles, which we know how to find the area of. Use rectangles to approximate the area. Okay? So finding areas and finding derivatives and antiderivatives. Might not seem very related, but they actually are very closely related, and it sort of is called the fundamental theorem of calculus that relates area to derivatives and antiderivatives. Okay, so it turns out that you only need f to satisfy a few properties to be able to find the area under the curve f of x between a and b. You only need f to be really continuous to be able to do that, but we're going to see that next week. But today I'm going to show you something we're going to need for next week, which is sigma notation. Okay. So when we're going to try and find these areas under curves, we're going to look at sums that look like this. S equals 1 over 2 times 10 squared plus 2 over 2 times 10 squared plus 3 over 2 times 10 squared, blah, blah, blah. So in each of these terms, really only one thing is changing, right? The numerator in each of these terms is different, but the denominator is the same in every term. So it's annoying to keep writing out the same denominator over and over and over again when only one part of this sum is changing. Okay, and so to get around this, we have what's called sigma notation. And it's a way to write all of these terms, in sort of one small little package. Okay, and so this is the notation that we use. The sum of n terms, which we're calling a1 and a2, all the way up to an, can be written as this letter here is called sigma. That's why it's called sigma notation. That is a capital sigma. Okay, and so we write the sum, I will usually say the sum of ai from I equals 1 to n. So the sum starts at I equals 1 and goes up to I equals n. And so all this means is you start off and you let I equal 1. Then, and you write that term down. Then you write plus, and then you go back and you let I equal 2 in here. And then you write that term down. And then plus, and then you let I equal 3. And then you write that term down. You write plus, and you do that all the way up to I equals n. Okay, that's all that this means. And so it's a quick way to write out something like this over here. So I think it's easiest to see what is happening with sigma notation by looking at some examples. So what are the following sums equal to? So we'll look at number 1 first. Sum of I, where I goes from 1 to 6. The sum, I goes from 1 to 6 of just I. Well, all this says here, each ai from before is I. So first I let I equal 1, and when I is 1, obviously. So I write down a 1, and then I write plus. Then I let I equal 2. When I is 2, obviously I is 2. So I get 1 plus 2 plus. Then I change I to 3, and I write the next term down. I is 3 plus. Then I is 4, and I write the next term down plus. Then I is 5 plus. Then I is 6. Okay. So simplifying this, I'm going to get 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. Okay. So number 1, we get 21 for the sum. For number 2, I'm looking at the sum. I goes from 0 to 5 of I plus 1. Well, this is going to be equal to, first I start with I equals 0. When I is 0, I plus 1 is 1. All right, plus. Then I increase I by 1. So now I is 1. Then I plus 1 is 2. All right, plus. Then I is 2, so I plus 1 is 3, plus. Then I is 3, so I plus 1 is 4, plus. And then we'll do when I is 4, we'll get 5. And when I is 5, we'll get plus 6. So this is the exact same sum we got before for the first problem, but we have a different looking summation, which is fine. You can write the same sum in different ways, is all this problem was trying to convey. Okay, and then we'll look at number 3. For number 3, we're looking at the sum j equals 3 to 7 of j squared equals. All right. Well, again, we start with j equals 3. When j is 3, j squared is 9. Yeah, I write a plus. Then I increase j by 1. So the index doesn't have to be I. It can also be j, and it can be any letter, really. But we usually use I, j, and k. Okay. So then when j is 4, I'm going to get j squared is 16. Yeah, right, plus. Then when j is 5, I'm going to get 25, which is 5 squared. Then I write a plus. Then I increase j by 1. J is 6, so I'm going to get 36 plus. And then when j is 7, I'm going to get 49. Okay. So then this is going to be equal to, well, 9 plus 16 is 25, plus 25 is 50, plus 36 is 86, and 86 plus 49 is, I don't know, 86 plus 49, 15, 112, 135, obviously, 135. Okay, so the summation notation is just an easy way to write out a sum where really only one thing is changing. You can write it out using this summation notation or sigma notation. Okay. So I will show you 3 more examples of this, and then that's gonna be where I stop this video. Okay, so what are the following sums equal to? Number 1, the sum j equals 1 to 5 of 1 over the square root of j equals, well, again, we start with j equals 1. So when j is equal to 1, I get the inside of the sum, I get 1 over the square root of 1. And I write plus. Then I increase j by 1 to 2. And then the inside of the sum is 1 over the square root of 2. Then I write plus. Then j is 3, plus. Then j is 4, plus. Then j ends at 5. So this is equal to 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1/2 plus 1 over the square root of 5. And that's how I'm going to leave it. Now, these next 2 are interesting. So number 2, we're looking at the sum j equals 1 to n. N is just some integer. Okay. And then 1 over n times k. Sorry, was it a k? It was a k. Sorry, k equals 1 to n. 1 over n times k squared plus 1. Okay. So here, even though we have 2 letters happening, the only thing that really matters as far as writing out the sum is the index. That's the only thing that's changing in each term. So when k is 1, you still just plug in k equals 1 inside of this, and that means that that term is going to have an n in it because I'm not plugging in anything for n. So when k is 1, I'm going to get 1 over n times, and when k is 1, I get 1 squared plus 1. And that's the first term, plus. Then I increase k by 1 to 2. I'm going to get, again, 1 over n times 2 squared plus 1. Then I increase k to 3, plus 1 over n stays there times 3 squared plus 1. Okay. And then I do this plus dot, 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 and then I do this all the way up to k equals n. We get 1 over n times n squared plus 1. Okay. So if you want, every single one of these terms have a 1 over n, so you could write the 1 over n out in front, and then you'd get 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 plus so on and so on and so on plus n squared plus 1. Okay. So this is the advantage of sigma notation, is I don't have to write these dots and just trust that you see the pattern. With sigma notation, all of these terms are sort of captured with this one group of symbols. Whereas over here, I've got dots that, again, I sort of have to trust that we all see the pattern. Okay. So this type of sum in particular is going to be very, very, very important for us in the next lecture. Okay. And lastly, number 3, the sum I equals 1. The sum I equals 1 to n of f of x I delta x. Okay, so again, the only thing that really matters here is I. So I start off with I equals 1. Well, when I plug in I equals 1, I'm just going to get f of x 1 delta x. And that's it. That's all I can write there. I don't know what f of x is. I don't know what delta x is. So this is all I can write for the first term. And then plus, then I increase I to 2. F of x 2 times delta x. Plus, then I increase I to 3. F of x 3 times delta x. Plus, and then I keep doing this all the way up to f of x n times delta x. Again, if you want to pull out, each of these terms has a delta x in common. So I could write this as f of x1 plus f of x2 plus f of x3 plus on and on and on plus f of xn times delta x. Okay. But that's all we can do without knowing a specific f or a specific delta x or specifically what x1 and x2 and x3 and x4 are. But this type of sum, for when we know specifically what f of x and delta x and the xi's actually are, is actually going to be kind of the most important thing for us for the next couple weeks. We're going to look at what this specific sum looks like and what we can get out of it. So with that, I'm going to end this lecture. You guys now have most of what you need to do the homework. I think there's 2 problems left that we will get to on Thursday. But that's everything that you need to do or need to be able to do the homework. So if you have any questions about anything I covered in this, please send me an email. And I'm responding to emails all day. So thank you all for watching this, and go vote.